Hi everybody. Today we're going to be working on this section, which is applications to physics and engineering. Now, what we're going to talk about first is going to be hydrostatic pressure. All right, and one of the items I want you to think about when you're thinking about hydrostatic pressure is that imagine that you're submerging some sort of object into a body of water. All right. The further that object goes, the more pressure that is being placed on that object because of the depth that is being displaced. All right. Naturally, one of the ways that you want to think about this is thinking of a dam. A dam holds water from moving freely to another place. And if you notice, when dams are built to be thicker the lower they go. So at the very top, they start off kind of quote unquote thin, and then as you start moving lower towards the bottom of that dam, the dam starts getting bigger and bigger and bigger. This is because the water pressure that is being put on the dam has a greater force the lower it goes. All right, and we want to investigate that. So on here on screen, what I have this little watermark here. And what we're going to do is we're going to submerge this one plate, let's call it plate A, and it's going to be submerged a certain amount of distance. Now this plate A, I'm going to denote here as the area of this plate. Alright, so that's going to be the area of this plate. Now in order for us to determine what we're going to be looking at here, if we automatically consider the volume of the object that is being made here, well, the volume is just going to be the area multiplied by the distance that it was displaced, and then we're going to be able to calculate the whole volume that this piece of this area is actually encompassing. All right. Now, it's not necessary to think about the whole volume here in this empty space. We'll clarify that a little bit more as we keep working through. All right. One of the items that I do want to illustrate here, or that I do want to talk about as well, is that we want to look at mass. We want to look at the mass of an object. So the mass of an object is going to be rho multiplied by some sort of volume that object is being made of. All right. Now, rho is a Greek letter, and this is going to stand for fluid density. All right. So this is going to stand for fluid density. Anytime that we're looking at fluid density, we're always going to think about rho. All right. Now, as far as mass goes in this particular sense, whatever fluid density we have, whether it be water, oil, anything like that, we can always take a density of that said fluid. All right. We have milk, olive oil, seawater, fresh water, mercury, gasoline. We have different types of fluid that we can submerge different objects in. So we always have to account for that fluid density. All right, and then the volume, well, the volume is going to be the volume of that object that you are submerging in there. All right, so once we have this, then we can clarify this a little bit. We can actually write this as rho multiplied by volume, but volume by up here was thought of as area times density, or sorry, area times distance. All right, that was this piece here. Perfect. Now, if we want to calculate force, if you remember, force is just mass times acceleration. But since we're going to be submerging items, force is just going to be mass times gravity. All right. Now, under the assumptions that we're working on here, force is equal to mass times gravity. Well, mass from up above here, we were given that mass was actually rho, that fluid density, multiplied by the area, multiplied by the distance that it was being submerged. All right, so here we have this force that we're looking at. All right, now, excuse me. Now, my apologies, I forgot gravity here. There we go. My apologies. Now, gravity. We're going to have two different interpretations of gravity. Now, the two different interpretations of gravity are going to come whether we're using the US customary system or the metric system, otherwise known as SI units. So we have to identify what are we working with. Are we working with metric or are we working with US customary? The metric system is otherwise known as your SI. Typically you hear this in engineering a lot, engineering and physics, you use SI units. SI units basically stands for System International, which means that's international system of units, which is used all across the world. The US has their own measurements, and they're kind of ass backwards. So we'll keep going from there. So if we have gravity, as we do in here, under the metric system, gravity, we're going to be using the approximation of 9.8 meters per second squared. And if we're doing the US customary, then we're going to use the approximation of 32 feet per second squared. All right, so that's just something that we then have to then just think of, and we have to use when we're looking at these specific items. All right, now let's talk about pressure. What type of pressure is this going to be exerting? Is the water or this liquid or this fluid going to be exerting on this specific object? Well, in order to do that, you have to take the force that is being applied on the object, and you got to divide it by its area. Take the force that's being applied divided by its area, and you get that equal disbursement. But in that particular sense, this is just rho times A times the distance times gravity divided by its area, which means the pressure here is just going to be rho times the distance times gravity. And this is how we define pressure. Pressure is just going to be this particular instance. All right. Now, we can always go back and we can always modify it slightly different. But in this particular case, we always want to keep pressure as your rho multiplied by the distance that it's being submerged multiplied by gravity. All right. Now, one more specific item here when we're talking about pressure. All right. So for pressure, again, if we're using the metric system or if we're using the US customary, we're going to have slightly different versions. All right. So if we're using pressure for the metric system, pressure in the metric system is going to be rho multiplied by gravity multiplied by that distance that's being displaced. If we're going to US customary, pressure is just going to be delta multiplied by its distance. Delta here, excuse me, oops, my apologies. Here we go. Delta is the weight density of the object. All right, so we got to kind of keep that in mind, that delta is going to be the weight density. Now, again, we always, in the U.S. customary system, we got to be careful because in the U.S. customary system, we typically don't account for gravity when we're talking about for the pressure, versus the metric system needs to account for that gravity. All right, so we got to be really, really careful with that. All right, now a few more items that I'm going to explain here, and these items are going to be stuff that you do need to know because we're going to keep using them quite a lot. For the water, when we're looking at mass density, in other words, rho, all right, so fluid density here for water. Oops. For water, this is going to be 1,000 kilograms per cubic meter, or we can say that at this particular case, water has a weight density of 62.5 pounds per cubic foot. All right, so these particular cases here that we have water being given to us in terms of either its weight density or its mass density, we then have to make that interpretation whether we're using the metric system or whether we're using the U.S. customary system. And the only way that you're going to see, or the only way that you're going to extract which system you're using, is by reading the problem. All right, so let's go ahead and jump into a problem. This is going to say that a vertical plate in the shape of a triangle is submerged in water. What we want to do is we want to express the force as an integral and evaluate it. All right, and I'm going to show you the picture below. All right, so the picture is going to be shown below. Now, I'm going to put pause on the video, I'm going to draw the picture, and then I'm going to come back. All right, here you are. So we have this right triangle being submerged into the water. So it's going to be fully submerged 2 feet after it's broken the plane of the water. All right, here the blue denotes the water, and then the plate's being submerged 2 feet below that. And then this height here is another 5 feet, and then this distance here is going to be 10 feet. All right, so now what we want to do is we want to express this force as an integral, and we want to be able to evaluate this specific force. All right, so as we start looking at this, we then have to start extracting a few items. All right, the very first thing that I want to observe is that they're giving me all of my units in feet. So all units are in feet. Because of all units are in feet, this is going to tell me that I need to use the U.S. customary. So I'm going to use a U.S. customary system. All right. If I need gravity, then I'm going to interpret gravity as 32 feet per second squared. Anything else that I need needs to be in that U.S. customary system. All right. So awesome. Now that I have that, what I want to do at this point in time is I want to figure out what is the pressure occurring at all of these different points. All right. So I want to figure out what's the pressure occurring here, what's the pressure occurring here, occurring here, occurring here, and that's going to be from any direction when you're being submerged. All right, so think about a three-dimensional object being submerged, or just think about your head being submerged. When your head is being submerged, you can feel the pressure of the water being exerted on your face, right? Whether it's your mouth, your nose, your ears, your eyes, whatever that may be, it's all going to have an even disbursement of pressure depending on the depth that you're going. And that's what we're trying to analyze here, is what is that even disbursement of pressure that we're looking at. All right, so in order to do that, what I need to do is I need to pick some random sample point within here. Now, I can't exactly do that without setting some sort of axes on here. So what I want to do is I want to set some sort of axes here. All right, so I'm going to go ahead and I'm going to draw my axes in here to signify that that's going to be the axes that I'm going to be using. Now, would you all agree with me to say that this object is being submerged downward? If yes, then that's awesome. So what I'm going to do here is I'm going to just create an axis, and I'm going to center my axis here. There we are. So this is my axis. Now, this is going to be my x-axis. This means that I'm orientating. This means my axis is orientated downward for my positive x direction. Now, where is 0? Well, I'm going to consider 0 here. All right, so that's going to be x is equal to 0, and the positive values extend downward now. All right, so again, I'm just illustrating my axis in a slightly different way. Now, how would my y-axis look like? Well, we're free to choose how our y-axis is going to look like, or in other words, what way it's increasing. I can choose this to say that this is going to be the way my y-axis is going to be increasing, naturally, because from the x-axis, this 10 extends this way, and it gives me just a positive value. All right, so awesome so far. Now, again, the process that I want to do is I want to create some random sample point, and that's exactly what I'm going to do. Is I'm going to go through and I'm going to find some sample point here. Let's say it's this sample point. It's a little bit convoluted in there, so I'm going to extract it over here. This is going to be my sample point x sub I star. All right. So the pressure that I'm going to be looking for, or the pressure that I'm going to be analyzing, is going to be the density of the water that I'm looking at here. And again, I'm just going to keep denoting this weight density of the water just as delta. All right. So I'm looking for my pressure here. My pressure is just going to be delta multiplied by that initial sample point. So my pressure is that weight density of the water multiplied by that specific point that's going to be here. All right, nice, not too bad. All right, but now we got to calculate the area for this plate, right? Now, the area is constant, you are absolutely correct, but the pressure is going to be exerted differently depending on what depth of water, or depending on what depth inside of the water that plate is in. So we then have to figure out how to break down the area of this specific rectangle into smaller pieces. Well, that's where calculus comes in, at least Calc 1. In Calc 1, we actually went through a whole process of breaking all of this down to say that we had really tiny rectangles here, like such. All right, so we have this tiny rectangle here, and we want to find the area for that rectangle. Oops. So we want to find the area for that rectangle. Find the area for the rectangular strip. All right, so let's go through and let's find the area, and we're going to find the area in terms of this x sub I star. All right. So what's really nice about this is that we already have a few items that we can use. All right. This in here, this point, this ordered pair, this is going to be in the x coordinate. What is that, 7? Yep, 7, and then up in the y direction by 10. So naturally that's 7, 10. This ordered pair here can be thought of as the x coordinate just moving out 2. Y coordinate must be 0. All right, nice. So let's see if we can go through and if we can solve this equation here. Now, the reason I want to say is that we need to solve this equation is because, again, I need to find the area of this little rectangular strip that we use to break up all of our triangle. All right, so let's go ahead and let's find that particular length or that particular equation. All right, so I have 2 points, which means I can find a slope. I'm going to use slope here, which is going to be y2 minus y1, so it's going to be 10 minus 0 divided by 7 minus 2, which is 10 over 5, which is 2. Good so far? Nice. All right, now I'm going to use my equation, y minus y1. So I'm going to use the first equation here. So y minus y1 is equal to your slope times x minus x1, which is 2. Which means the equation here gives us 2 times x minus 2. Awesome. Now, why do I need this? Well, I said that I wanted to find this particular length of that rectangle. And the particular length of that rectangle for this sample point is just this equation. Because again, it's the width of that rectangular object inside of that triangle. So the length that I want, or the area that I want, the area is just going to be this piece, which is, are you guys okay if I distribute? I hope so. There we go. So the area is just the length, which that was that 2x sub I star minus 4, because that was that sample point, divided by the height here. But remember from calculus, if we did the height here, if we subpartition this interval into smaller pieces, the width is just going to be delta x. All right. So to see this a little bit more clear, I'm going to extract that rectangle down here, and I'm going to enlarge it. All right, this piece here was delta x. X sub I star fits somewhere in here. So it's just some random sample point that we have. All right, and then the length of this object is this specific length here, the one that we just found. This is that 2x minus 4. So naturally, when we want to find the area, it's just delta x multiplied by 2x minus 4, which we have here, specifically denoted that it's for the sample point. Awesome. All right, now we're on the right track now. So let's go ahead now that we have this area. Now what we're going to do is we're going to find the pressure or the hydrostatic force. Hydrostatic force being exerted on the rectangular strip. All right. So if we want to find that hydrostatic force being exerted on the rectangular strip, what we're going to do is we're going to take the pressure that we found, this pressure, and we're going to multiply it by the whole area that that strip has exposed. So in this particular case, to find that hydrostatic force, all we're going to do is we're going to take the pressure and we're going to multiply it by the area of that rectangular piece that we found. So this is naturally going to be delta multiplied by x sub I star multiplied by 2x sub I star minus 4 multiplied by delta x. Here's our density, here's our pressure, and then here's the area. Now again, that's only for that one small little strip. That's only for this guy right here. All of that triangle, we split the height of that triangle into small n little pieces, which means if we wanted to get a good approximation, of the hydrostatic force, on the triangle, then what we're going to do here is we're just going to take a big summation. We're just going to say, okay, well, let's go ahead and let's find all of these sums that we just analyzed here for all of these rectangular strips. Like such. But again, this is just an approximation because we're taking a whole bunch of these mini little strips that we've cut them into n values. But again, in calculus, we tend not to want these approximations. We tend to want exact values. So if we want the exact value, all I have to do now is apply some limit. All right. So I'm going to now say find the exact value of the hydrostatic force on the triangle. And this is the last piece that we need to do. So to find this exact value, then we're just going to take an infinite amount of these subdivisions and work with that. X sub I star multiplied by 2x sub I star minus 4 multiplied by delta x. But lo and behold, this piece right here, that's just your Riemann sum. Riemann sum, according to Calc 1, has a definition that says that we can go ahead and write this Riemann sum as an integral. We just have to figure out what are the bounds. Well, the bounds were only being subdivided for the triangle that was being submerged. And the triangle was being submerged between 2 feet and 7 feet here. All right, so we're going to go through that. So from 2 to 7, we're doing this integration. There we are. Looking good so far. All right, so from 2 to 7, and then this delta, remember, delta, that's our constant. So delta multiplied by x multiplied by 2x minus 4, and this delta x is just my dx. Which means this should be able to find my hydrostatic force. And this is my first answer that I want to look at. All right. Now, specifically because here on the question said express the force as an integral. So we expressed this hydrostatic force as an integral. All we have to do now is evaluate it. All right. So I'm going to go through and I'm going to keep delta as a constant. So delta is going to multiply the integral from 2 to 7, distribute the x. So that's 2x squared minus 4x dx. It's going to be delta multiplied by, in this case, it's going to be 2/3 multiplied by x cubed minus 2x squared. And this is going to go from 2 to 7. Good so far? So delta is going to multiply 2/3 multiplied by 7 cubed minus 2 times 7 squared. All right, good so far. Minus 2/3 multiplied by 2 cubed minus 2 times 2 squared. Oh, sorry, that's not a minus, that's a plus because the minus gets distributed. Awesome. So I'm going to go through and I'm going to find out what this is. All right, so here I get that delta is going to multiply 400 over 3. And now I can go ahead and substitute what delta is. Delta was that water that was being submerged. And again, let's say that the problem didn't give me that it was being submerged in water. All right, so the fact that it's being submerged in water is right here. Say that it said that it was being submerged in mercury or milk or olive oil or seawater or fresh water. Depending on what type of water we're looking at, we would then need to use that different water density here. All right, but since it was just water, we're just going to go with 62.5, and this is going to be pounds per cubic foot multiplied by 400 over 3. Now 400 over 3, that was these x's here that we're looking at, all right, which means this is just going to be square foot. All right, looking good so far? All right, actually give me 1 second. I don't think that's going to be square foot here. Yeah, it's not going to be square feet. All right, it's actually just going to be cubic feet because we have one that's cubed here. My apologies. There we go, cubic feet. And now all I do is multiply. When I multiply, I actually get an approximation here. My approximation here is going to be 8333.3, and this is going to be pounds. So the force that is being applied on this triangular shape that is being submerged in water is 8,333.3 pounds. Awesome. So that's how we talk about that's how we talk about force, or specifically hydrostatic force, in this section. All right, awesome. All right, and so if you look at your book has different examples that you can go through, and hopefully you can follow along with those examples. They're going to be very, very similar. All right, now just to keep in mind here, if you follow along with this, some other books or some other professors might have a different technique for finding this specific length here. However, they should all come up with the exact same answer, which should be 2x, or 2 times the quantity of x minus 2. All right. Some different professors like to use similar triangles here. If you have similar triangles, then you can solve for the missing side, which means you're going to be able to get that specific value. All right. So what I want to do next is I want to move on from hydrostatic force, and I want to move on into a center of mass. All right. So to find the center of mass, I need to give you an illustration. That way we can start with that illustration and then start moving towards more of a better method to find the center of mass. All right. So give me a few seconds and I'll prepare that illustration for you all. All right. So here's my depiction here. So what I want you to do is I want you to imagine here that we have some sort of scale that is balanced on the tip of this triangle. All right. On one end of the scale, we have what is known as mass 1, and at the end of the other scale, we have what's known as M2. Now, this scale is going to be perfectly balanced. All right, and because it's going to be perfectly balanced, it's going to be balanced at its midpoint. All right, its midpoint determined by the amount of weight that M1 and M2 are adding to it. All right, so we then need to figure out what is that midpoint. If you notice, the notation that we use, this X bar, if you've ever taken statistics, you still use the same notation for the midpoint. It's X bar, otherwise known as the average, otherwise known as the mean. So we need to make some interpretations here. All right, we need to be able to find that. So what I'm going to do here is I'm going to start looking at these different items. All right, I'm going to say that M1 is positioned here at X1 and M2 is positioned here at X2. And the distance being made between where we're at here is going to be some distance 1, and the distance being made here from the midpoint all the way over to here is just going to be d2. Now, if this is perfectly balanced, and it is, all right, then we're going to be looking at the fact that mass 1 multiplied by distance 1 must be equal to mass 2 multiplied by distance 2. All right, so let that sink in for a little bit. We take mass 1, we multiply it by its respective distance away from that balancing point. Take mass 2, multiply by its distance away from that balancing point. Since it's in equilibrium, they should both be equal to one another. Great. But we have an added bonus here that when we talk about distance 1 can be interpreted as x bar, in other words, that balancing point, minus x1. And m2 times d2, well, d2 can be thought of as x2 minus x bar. Nice. Now that we have this, let's see if we can find what that x bar is. In other words, what is that one balancing point that we then need to place our scale on to keep this balanced? All right, so in order to do this, we're going to have to go through and we're going to have to distribute m onto both sides. All right, this is going to be mass 1 multiplied by x1. This is going to be mass 2 multiplied by x2 minus mass 2 multiplied by x bar. Again, I'm trying to solve for x bar, which means I need to get x bar by itself. So that's going to be m1 x bar. I'm going to add this over. That's going to be plus m2 times x bar is equal to m2 x2. And I'm going to bring this over, and that's going to be plus m1 x1. Nice. On the left-hand side, I'm going to factor out x bar. And we have mass 1 plus mass 2 is equal to mass 2 times x2 plus mass 1 times x1. And we finally arrive at a conclusion. The conclusion being that x bar can be found by taking mass 2, multiplying it by x2, adding that to mass 1 multiplied by x1, and then dividing by mass 1 plus mass 2. Interesting. Now, I want you to just observe this for a minute. You want to observe this because this plays out on a huge scale, right? This isn't just talking about what is that balancing point. This is actually giving us a really good way as to how to find balancing points on these objects that we can think of. Think about this particular line being a car, right? The front of the car has a little bit more weight because of the engine. The back of the car doesn't have that much weight. So how would we then be able to calculate what is that specific balancing point? Well, if you take the weight of the front axle, take the front weight of the back axle, divide it by their positions that we're measuring, x1 and x2, and then all of a sudden we can find where that balancing point is for the car, at least tie-down wise, in a one-dimensional aspect. So this turns out to be really, really interesting in how this is all playing out. Now, we have to be careful here. These specific items, I'm going to call M2, M2, X2. So M2, X2 and M1, X1 are called moments. More specifically, they are called moments about the y-axis. Now, why is it called about the y-axis? Well, I want you to follow me along here. What if I center my vertical line here to just be the y-axis? Would I then be able to calculate how far these distances are, in other words, x1 and x2, based upon the y-axis? The question is, or the answer is yes, I will be able to figure out what is that distance based on the y-axis. That's why these are called moments about the y-axis. All right, so we just got to keep that in mind. Now, what this is talking about over here specifically, to find the midpoint or the balancing point, we need to add all the moments. What do we need to divide by? M1 plus M2. Well, M1 plus M2, we're going to divide by the total mass. If we know what mass 1 and mass 2 are, then we can just divide by the total mass. So naturally, we start getting this nice aspect of finding this midpoint just by analyzing what is the mass of these objects and how far are they away from the y-axis. So I'm going to start defining the moments that we're going to be using. We're going to be looking at the moment of the system about the y-axis. These moments, we're going to denote moments, capital M, sub y, that's going to be around the y-axis. Well, that's going to just be the summation of all of the moments that we're going to be looking at that are going to be moving away from that y-axis. All right, and we're just going to take that total sum. We're also going to be looking at the moment. Wow, I can't spell today. Moment, there we go, of the system about the x-axis. Now, this is more for a two-dimensional aspect, right? Now, if we're talking about the moment of systems about the x-axis, now we got to figure out how far are these points. Instead of being on a one-dimensional plane, now we're going to give them a y direction as well and allow them to change in that y direction. So when we look for moments about the x-axis, we're just once again looking to see how far are all of these masses with their distances being displaced. So in this particular case, it's still going to be m sub I because you're still looking at the mass. However, you're going to be looking at the y components. How far is each y component moving away from the x-axis? And then we'll be able to grab that. All right, awesome. Now, in this particular case, we can then talk about a little bit more specifically x bar. X bar can now be thought of as, well, in this particular case, just the summation, summation of all the moments about the y-axis. So that's going to be this guy here. So we're going to take all the moments about the y-axis and we're going to divide it by the mass of the object. All right. Now, your y values can be thought of as the same thing, right? If I want to find the midpoint or the balancing point for my y values, then all I got to do is take all the moments about the x-axis, because again, that's how far my x values are moving, and then just divide it by the mass of this object. Therein lies what we need. If you remember back from algebra class, we actually had a midpoint formula. The midpoint actually finds the middlemost point of a line segment. In other words, a balancing point for the line segment, given that there are no masses involved. If this is the case, then the midpoint was naturally the ordered pair x bar, comma, y bar. And we're going to keep using that notation. We're going to keep using that notation to identify what is known as a centroid. A centroid is basically the midpoint of this object, whether it be a line, whether it be a piece of lamina, whether it be a ball, whatever it may be. This is going to be a centroid, and we're going to be able to calculate what is that center of mass. Center of mass, sometimes it's abbreviated as COM, center of mass. All right, so now that we got more of an understanding of what it means to be this center of mass or to find the centroid, all we now have to do is figure out, how do we find these moments? How do we find these moments and how do we work with them? All right, so let's now transfer that into more of a calculus aspect. How do we want to work with it when we're given functions or when we're given pieces of lamina to work with? That's what we're going to investigate next. All right, so let's talk about this centroid or the center of mass for this piece of lamina or this object that we're going to be looking at. So I'm going to say here that I'm going to have some sort of function here defined on x and y axis, and we're going to further define an interval here, call it the interval from A to B. And because I'm defining this interval here, that means that I can find the total area underneath this specific curve. All right, so when I'm looking at the area for this, or let's say the mass for this, the mass of the object we can find rather, I should say, straightforward when we're looking at the center of mass, or sorry, when we're looking at the mass of this object here. All right, so the mass for this piece of lamina, which I'm just going to label A here. A is going to be for area. The mass of this is just going to be the density of the object multiplied by its area. But if you remember, how do we find the area? We find the area here by using calculus. It's just the integral from A to B for the function of f of x dx. So there's the mass of that piece of lamina. All right, so that's awesome. Now we got to focus on what is this x bar and what is this y bar, and how do we go about finding them. All right, so what I'm going to do really quickly then is I'm going to start subdividing this interval just like we did in calculus. All right, so let's go through that subdivision. We're just going to start subdividing this interval into these smaller rectangles, and then we're just going to keep on doing it over and over and over again. All right, and what I want to focus on is I want to focus on one specific, let's say, point here. Let's call this x sub I star. If I focus on this x sub I star, then naturally what I've created is, or what I can create is some interval around this x sub I star. All right, now when I create this interval around this x sub I star, what I can do then is I can say this point here and this point here can be thought of as, let's say, x sub I minus 1 and x sub I plus 1. That way x sub I will be right in the middle. All right. Now, more specifically, I'll get into what I want that to be. And what I'm going to do is I'm just going to create a height here. Just like that. Or actually, I'm going to create a height slightly different. I'm going to create a height to there. And the reason I want to create the height through here is because what I want to do is I want to start collecting these midpoints. All right. So what I'm going to do is I'm going to transfer this point, x sub I star, I'm going to transfer this point just to be the midpoint between these intervals that I chose. All right. So choosing x sub I star, naturally, then we're just going to choose an interval around it so that it'll make this that midpoint. And once I'm able to find that midpoint here, then I'm going to be able to say, well, this is just x sub I, comma, your function evaluated at x sub I. Just like this. Nice. So what I want to do at this point in time then is I want to try to find the centroid of this specific rectangle. So that's going to be my goal right now, is to find the centroid of the rectangle containing, containing x sub I average. All right, or we could say x sub I star. There we go. Now, if this is the case, well then the centroid is actually going to be kind of nice here, because the centroid here, centroid for that rectangle here, well, the average of these two, that's just going to be x bar. All right, so that's just x bar. It's, again, how we defined it. And since we have a height here, and this is a rectangle that we've created with the height of the function evaluated at the midpoint, then naturally it's just going to be half that length, half the initial length of x bar. So there's the centroid, and this is going to be the centroid for that one rectangle. Now, again, we don't want just a centroid for one rectangle. We now want to find what is the centroid for all of these individual rectangles, and that's what we want to focus on. All right, so the one thing that we want to then start analyzing is, in order to carry this on, we now need to figure out what are the moments of this region. All right, so we need the moments for that region, and that's what I'm going to be looking for. All right, so let's go through and let's find the moments for the whole region. And again, we need to find two different moments here, because again, we need to find the moments with about the y-axis, and we also need to find the moments about the x-axis. All right, so this is where we start trying to look at all of those different moments that are going to be occurring. All right, so let's start looking at the moments for that whole region. All right, so here, oops, excuse me. I'm going to have these moments for the y-axis, and this is going to be for that region. All right, so I'm only going to be looking at here for one specific region, and that one specific region that I'm going to be looking at is going to be for this region in here. So I'm going to denote that in purple here. This region here, I'm just going to call R sub I. All right, so multiplied by R sub I, there we are. So I'm going to take all these moments. Now remember, all the moments that we're looking at are just supposed to be the mass of that object multiplied by all of the x movements that we're going to be looking at for the midpoints. Now mass is actually defined right up here. So we already kind of know what mass is. It's just going to be rho times A. So that's rho times A multiplied by x bar sub I. Now we can further start breaking this down, right? We're going to break this down in the sense that now rho, well, that's just going to be some constant, but then we need to figure out what is the area of this specific region. So the area of this specific region, it's going to be this piece, which is delta x. All right, so that's going to be rho multiplied by the area that was that delta x multiplied by its height, and the height is just f of x bar sub I. And that's the area that we're looking at here, and this is still multiplied by x bar, like such. Now, if I want to calculate all of these moments, right, not to get an approximation for one specific area, now I want all of the moments for the whole region. All right, so the moments for the whole region now, m sub y, this is going to be the limit as n goes to infinity. This is going to be for I is equal to 1, stopping at n, and this is going to be for rho f of x bar sub I multiplied by delta x multiplied by x bar sub I. Now this naturally, rho's a constant because again that's going to be the density that we're looking at. So that's just going to be rho multiplied by the limit of this piece here, but that's just the Riemann sum, which means it's just the Riemann sum from A to B looking at x bar So that's just going to be x multiplied by the function evaluated at x, and then that's going to be dx, just like this. Which means we're able to find all of the moments for the whole region, and these are the moments about the y-axis for the whole region. All right, so this was about the y-axis. Now we want to find what are the moments that still falls under that category. So find about the y-axis. Now we got to do it about the x-axis. All right, so we can again go through the exact same process of all of this. All right, now going through that whole process once again, but this is only going to be looking for the moments about the x-axis, which means how far do all my y values move away. All right, so finding all of those y values, how they move away, this is just going to be rho multiplied by, well, all of those center of masses there, and that's just going to be 1/2 multiplied by the function at x bar sub I squared delta x. And that's going to be equal to, again, this is a Riemann sum, that's rho. So this is going to be rho multiplied by the integral from a to b, and this is going to be 1/2 multiplied by f of x squared, and that's dx. So these are all the moments about the x-axis. So now I want you all to then observe what we have here, and I'm going to mark these down in red because these are going to be important. We have that mass is equal to this piece here. We have that all of the moments with respect to the y-axis are given by this equation here, or this integral. We have all the moments about the x-axis, which are going to be denoted by this integral here. So by the way that we defined the centroid right up here, we now have a process to define what the centroid is in terms of a piece of lamina. All right, so we can then start analyzing, or let's say further explaining, that x bar is 1 divided by the area multiplied by the integral from a to b for x dx. Y, at least y bar, will be 1 over the area multiplied by the integral from a to b, and that's just going to be 1/2 multiplied by the quantity of f of x squared dx. So this is how we find our centroid, or our center of mass, by using these items here. All right, notice there is no density embedded in this, because at the end of the day, when we divide the moment by the total mass, the densities just cancel out, which means density is irrelevant when we're trying to calculate, at least for this specific piece, of when our centroid of mass happens, when we have a function that can model the piece of lamina. So let's go through an example and let's look at this. So we want to sketch the region bounded by the curves and we want to find the exact coordinates of the centroid. And here goes part A. We're going to have y is equal to the square root of x, y is equal to 0, and x is equal to 4. Alright, so the first job that we're going to have here is that we need to go ahead and we need to sketch this particular intersection. So that's exactly what we want to do first. Alright, so start getting a grid going. That way we can go ahead and we can start viewing this and we can start analyzing what we're going to need. Alright, y is equal to 0, x is equal to 4. Looks like it's going to be in the first quadrant. So that's my y, that's my x. Let's get a scale going here. All right, that's 4. All right, that's 2. Perfect. All right, so y is equal to x, or sorry, y is equal to square root of x. Here we go, and then when x is 4, we naturally get 2. So here's my square root of x. There we are. Y is equal to 0. When we look at y is equal to 0, we just get a straight line. And this is your y is equal to 0. And then we need x is equal to 4. All right, there we are. Perfect. So here's our x is equal to 4. Now, the region that we're concerned with is right in here, which means we have to try to find the centroid for that region. In other words, we need to find that center of mass. So what I'm going to do is I'm going to start using the equations that we need. In order to find mass, I'm going to use the equation that we just built for mass, which was just the integral, or the area that I'm going to be looking for. It's just going to be the area for f of x dx. All right, so that's the first thing that I need to do. And let's go ahead and let's calculate that mass. Integral, this is going to be from 0 to 4. So from 0 to 4, nice. And then the height, f of x, that's just going to be square root of x. So I'm going to denote it as x to the power of 1/2, and this is going to be dx. Perfect. And then we add 1, and that's going to be 3/2. So it's going to be x to the power of 3/2, divide by that, so multiplying by the reciprocal, and this is going to be from 0 to 4, which then means we're going to have 2/3 multiplied by 4 raised to the power of 3/2. All right. Let's see what this gives us. Square root of 4, that's going to be 2. 2 to the power of 3, that's going to be 8. 8 multiplied by 2, that's going to be 16. So this is 16/3. Nice. So the area that we found here, this is the area that we were looking at here. In other words, that's going to be the mass of the object that we're going to be looking at. Since we don't have a density given for this object, we omit the density here. All right. But again, if we're looking for the centroid, again, we won't need that specific value. All right, now let's go through, and I want to now find what are the moments along the y-axis. So I'm going to say here moments about y-axis. These are the first moments I want. All right. So my moments about the y-axis, that's going to be denoted as m sub y, which is just going to be the integral from a to b, and this is going to be x times f of x dx. That's according to the derivation that we had right up here. So then m sub y is equal to the integral from a to b, again, from 0 to 4, for x multiplied by the square root of x, because that's going to be my function, square root of x dx. This turns into the integral from 0 to 4. All right, and then this is x to 1/2, and this is x is 1, so this is going to be x to the power of 3/2 dx. We integrate, and that means we add 1 to the exponent, so that's going to be 5/2 multiplied by its reciprocal, and evaluate from 0 to 4. Looks perfect. All right. Whoops. No. Here we go. Okay, perfect. So now all I have to do here is evaluate, and this is just going to be 2/5 multiplied by 4 to the power of 5/2. So square root of 4, that's going to be 2. 2 to the power of 5. That's going to be 32, I believe. Yeah, 32. So 32 times 2, that's going to be 64. So then this in here should just be 64 divided by 5. Like such. Nice. All right, so we got one of our moments. Let's go ahead and let's choose, or let's go ahead and let's find another moment. And that's going to be the moments about the x-axis. All right, so the moments across the x-axis or about the x-axis, then we know this to be the integral from a to b, and then this is going to just be 1/2 multiplied by the function squared dx. So that means my moments for this particular case, moments about the x-axis, this is going to be the integral from 0 to 4, and this is going to be 1/2 multiplied by the square root of x squared dx. This means that this is just 0 to 4, half is a constant, and I'm just integrating x. Looks pretty good. So this is going to be 1/4 x to the power of 2, evaluated from 0 to 4. Nice. Which means this is just going to be 1/4 multiplied by 4 squared, which is just 4. It's looking good. All right. Pretty good so far. Now all I have to do to find these specific, or this specific centroid, to find the centroid, all we do is we find x bar and y bar. But again, x bar was created from what we just said right up top, was this piece right here. So that x bar, that's just going to be your m sub y's divided by your m. And then your y bar is just going to be moments about the x-axis divided by m. Naturally, this turns into 64/5 divided by the mass, which was 16/3. Moments about the x-axis, that was 4 divided by 16/3. And then all we have to do is put this into a calculator. So 64 divided by 16, that's going to get me 4. So that's on here, so it's going to be 4. 4 multiplied by 3 divided by 5, so it's going to be 12/5. Nice. And then this part in here, the 3 is going to go up top, and that's going to be 3/4, I believe. There we are. So here's the exact coordinates. The exact coordinates of the center of mass is at 12/5, comma, 3/4. So let's find the center of mass really quick. So 12/5, that's about 2.4. So 1, 2.5. So 0.4 should be somewhere around here, and then 3/4 the way up. So if this is 1, 3/4 of the way should be somewhere here. That's your center of mass. Which means if we were to cut this out, that's where that paper or that cutout, that region would balance at that specific point. Nice. So let's go on to the next example, part B. Y is equal to 2 minus x squared, and y is equal to x. So we now have this intersection occurring here, and we now want to figure out what is then that center of mass going to be. So once again, we go through the whole intersection process. We have to go ahead and we have to graph their intersection, and then we're going to start observing what it is that we're going to be looking at. All right. So here, this looks like a parabola that's opening downward. This looks like just a line, y is equal to x. So my centroid my area likely goes into quadrant 2, maybe even quadrant 3, all the way to quadrant 1 for my intersection. So I'm going to make sure I denote that here. Trying to line this up perfectly. There we go. Now let's move this here. There we are. And I'm going to give this a good scale. Okay, here we go. So what I'm going to do is I'm going to graph y is equal to x first. That way I can see what y is equal to x doing. What is it doing in comparison to my function. And that way it gets me a little bit more insight, getting all this done quicker. Stop moving. There we go. All right, here we go. So this is y is equal to x, looking nice. Y is equal to x. Now the next one that I'm going to do is y is equal to 2 minus x squared. So 2 minus x squared, that's a parabola opening downward with the vertex up at 2. And so at this particular time, I want to figure out what are the values for the x-axis when it's intersecting there. All right, so noticing that, we just need to solve for x. So that's going to be, if I place 0 here, move x squared over there. So that's going to be positive or negative root 2. So positive or negative root 2, that's going to be about 1.4. All right, so it's going to intersect somewhere around 1.4. So somewhere around here and somewhere around negative 1.4. So somewhere around there and there. Now let's figure out where the curve, where that parabola is going to intersect this curve. All right, so let's see if we can figure that out. The first thing I'm going to do to try to figure that out is I'm going to set them equal to one another. All right, let's see. Let's erase this here. It's a little bit too far. It's okay. All right, so let's go through, set them equal to one another. So this means that x is going to be equal to 2 minus x squared. This means that x squared, so x squared plus x minus 2 will be equal to 0. All right, this looks like it might be x plus 2 times x minus 1 is equal to 0, which means the intersections happen at x is equal to negative 2 and x is equal to 1. Nice. So x is equal to 2, somewhere down here it intersects, and at x is equal to 1, that's where it intersects. Perfect. So there's my parabola. Nice. Now again, the region that we're focusing on is a region right in here. All right. So again, the first thing that we're going to have to do is we're going to have to find the area. That way we can interpret that as the mass, right? If we were, again, given a density for this object, whether that object is a piece of steel, whether it's aluminum, whether it's wood, whatever it may be, it's going to have some sort of density. All right. So at this point in time, let's go ahead and let's find that mass, since that's going to be one of the easier ones to do. This is going to be the mass. It's just going to be the integral, and I'm going to integrate with respect to the x-axis. So the x-axis looks like it's going between x is equal to 2 and x is equal to 1. So negative 2 to 1. And then I'm going to do the top function minus the bottom function to make sure that we get this area right in here. So the top function, that is your parabola, which is 2 minus x squared, minus the bottom function, which is just y is equal to x, like such. And then this is all going to be dx. All right, that's going to be negative 2 to 1. And then that's just going to be negative x squared minus x plus 2 dx. All right, let's see what this gets us here. So going through our calculations, let's see, that's going to be negative 1/3 x cubed minus 1/2 x squared plus 2x, evaluated between negative 1 and 2. There we are. This should give us, I believe it's 9/2. There we are. All right, so I'm going to say dot, dot, dot. We did some work and we found that it's 9/2. All right, and again, you can verify this on your own. Now, what I'm going to have you do is I want you to complete the rest of this and put your answer in the discussion board. All right. Now, when you work with the centroid here, we're going to find some moments, all right, just like we did right up here. So the moments about the y-axis, and these moments about the y-axis, again, what we're looking at here for my moments about the y-axis is going to be the integral from -2 to 1. All right, it's looking good so far. Now, since I have this moment about the y-axis, again, what I'm going to do is I'm going to start looking at all of my values right in here. All right, so this is still going to be x, but instead my function is the area that is being bounded here. So the function that I look at is the top function minus the bottom function in order for this to occur. So that's going to be 2 minus x squared minus my bottom function, which is just x, like such. Once we're able to get this, we'll then be able to calculate what is that moment about the y-axis. All right, so now that I have this set up, you can go ahead and you can finish that off. The moments about the x-axis. The moments about the x-axis, so this is going to be m sub x. This is once again the integral from -2 to 1. And in this particular case, this is going to be 1/2 multiplied by the function that's bounding the area. The function that's bounding the area, once again, is top function, 2 minus x squared, minus the bottom function, which is just x. And that whole quantity, or sorry, we're going to make sure that we square these two quantities. So it's that quantity squared minus this quantity squared. And we should be able to get that specific value for that integral for dx. So again, I want you to finish this off. Now, on the discussion board answer that I want to see is, what is your center of mass? In other words, what is that centroid? All I want to see is the ordered pair. What number goes in here and what number goes in here? That is a question that you must answer. And in order to answer that question, you must go through this whole process of the integration techniques. All right? So that's going to wrap it up for this particular section. I hope you all enjoyed it, and I'll see you all for the next one.